So, greetings everyone. My name is Pushkar Navle, and I'll be presenting the project of MCMS subject, real-time monitoring of manufacturing systems using IoT and cloud computing. The team members are Siddharth Krishna, Vinit Malik, and myself, Pushkar Navle. So, first of all, what is cloud computing? So, basically, cloud computing is a new way of cloud manufacturing. Cloud manufacturing is a new way of manufacturing. So it uses cutting edge technology to enable full sharing of manufacturing resources. So some of the most important technologies use the cloud computing and internet of things, IoT. So lots of attention has been given by academic people as well as many practitioners all around the world right now, and this offers a great scope for improving the manufacturing processes. So now exactly how will it be helpful for the manufacturing companies? So there are many resources in any company, such as the workers, machines, production lines. So company has to monitor them and it has to make sure that all the resources are utilized properly. So these resources are converted into SMOs. SMOs means smart manufacturing objects. So these objects are able to sense and interact with each other because of their smartness. So one example is RFID, radio frequency identification. So many times in many of the companies also, this RFID is used to take attendance. It is used for monitoring many aspects. So this is there, and it also helps the data sharing of machines which are actually working. So for any manufacturing unit, the machines are the most value adding objects, and this helps us to monitor and share the data related to the machines, like how the machine is functioning, how long it has been functioning, what is its performance, and does it require maintenance, and all these various factors they come up with. So what are the challenges which are faced during this, or which are generally faced by the manufacturing companies? So the first challenge is it is very difficult to label so many manufacturing units. There are so many manufacturing units in any manufacturing company, so it is quite difficult to label all of them. There might be many small and big units. So that is first difficulty and challenge which is faced. And while using the barcode also, barcode technology is generally used for identification. So while using that also, it is quite difficult because on the field, when the shops are used, shops are working, so many times dust and oils they accumulate over the RFID, they accumulate over the RFID tags, and that makes identification quite difficult. And also the companies, they are very interested to know who did what, when, where, and why they are doing. So these 5W questions, many times the companies ask. Many of the times the donors, the people who are investing, they ask the manufacturing company. So earlier this was addressed by traditional methods such as personally calling the people, then offline monitoring and all these things. But that is quite old fashioned, and not precise information was given, not precise information was not received, as well as it was not timely. It used to take a lot of time. So these are the common challenges which are faced. So to address the above challenges, we propose to use IoT enabled real time machine status monitoring approach for CMFG, so that these 5W questions can be very easily answered. So first of all, we deploy various RFID readers and tags at various sites so that the resources can be identified. And when the data is generated using this RFID readers, so that is captured, sensed, and that is processed to generate useful schemes, which will be very helpful later on for planning and rescheduling. So this real-time monitoring helps us to generate schemes which are based on the actual data, what is happening on the spot, on the field. And finally, using this generated data scheme, we use cloud-based services. So this data is put on the cloud and the processing is done further. And using the smart view, we can see the entire data and we can visualize the real-time status of the working machine. So whatever is happening on the site, exactly what is happening on the machine, that can be monitored to a large extent using this technology. And that helps the company to improve its products, see its faults, and take further steps using the monitoring for its development and advancement. So this is the introduction from my side, and I hand over the video to my teammates so that they can take it ahead. Thank you.
Hello sir, this is Vineet Malik and I'll be presenting the overall architecture and conclusion of our project. The overall architecture of our IoT based real-time monitoring system consists of 4 layers. The first layer is made up of smart machines. This layer gives us the ability to sense and adaptively react uh, according to production tasks. It also helps us uniquely identify each machine component using RFID tags. The components of this layer are machine parts that are embedded with sensors and the sensors which can be like RFID readers and tags, vibration sensors, temperature sensors, etc. The second layer is called smart connection. This layer helps the smart machines to communicate among themselves and collect the real-time manufacturing data from these machines. To do this, we use different kinds of networks based on different kinds of sensors, like we use Wi-Fi, wired connection, radio waves, and 4G network. The third layer in this architecture is data model. This layer is used to standardize the data we collect from the first 2 layers of smart machines and smart connections. There is a huge amount of data that is generated during the manufacturing. To be able to use that data to make good decisions, we need the data to be in a standardized format. This layer does that job. Based on the machines, we use 3 different kinds of data modeling formats. First is MT Connect, which is used for information from numerically controlled smart machine tools. Second format is STEP, which is used for exchanging data among various information systems such as CAD, CAM, and product data management systems. Third format is XML data format. It is used to organize data schemes so that further applications like the mobile applications which we will host on the cloud can use it for data sharing and exchanging under different situations. On top of these 3 layers is the layer of smart view. This is an end user layer which is responsible for helping the person, uh, like the manager of the manufacturing plant, understand the information which is coming out of this real time monitoring system and make decisions using that. This layer provides 3 kinds of views for that purpose. First is real time machine status, in that we can know the status of the machines, the like who is operating the machine and which component is being processed on a live basis. Second is statistics report, which we use historical data to generate reports, which can then later be used for production planning. Third kind of view is augmented reality based visualization, where the information is attached to the machines in the view.
So this section presents a case study for demonstrating how our proposed IoT-enabled real-time machine status monitoring solution is facilitating the operations of our manufacturing shop floor. So we are presenting a case study on that. So this is our laboratory test bed description. So the laboratory test bed, it includes two milling machines. It includes two KUKA robots, which are placed in an area around 20 meters square. And there are several buffers for milling machines, which are used for holding limited workpieces. And two robots are fixed up there, and there is some conveyors that are responsible for moving the various components. Now, in this in this monitoring, there are a lot of challenges which we are facing in monitoring the machine status in real time mode. Like several challenges were being contemplated upon. In the first place, there is a large number of manufacturing resources involved in the test bed, which includes machine tools, cutting tools, various materials, workers, production order, and you know, and so many other things. So, how to identify these resources systematically and effectively, that was a big issue. Secondly, how to facilitate the production operations and how to facilitate the production operation behaviors by assistance of the deployed IoT devices so that the real-time manufacturing data could be captured and collected. And moreover, thirdly, how to organize various heterogeneous data from the different objects so that a visualized monitoring approach could be achieved. So these were the few of the challenges which we are facing. So we designed the solution in this way. In order to address the challenges, there were following sections. We are divided into two sections that demonstrate the creation of a cloud manufacturing shop and how to use the deployed IoT facilities in real-time monitoring machine statuses. So first is this creation of cloud manufacturing shop. So the creation of the cloud manufacturing shop, it was achieved in several steps. So first step was deployment of IoT device. So different IoT devices were deployed in the test bed that is converted into a cloud manufacturing environment. Firstly, each machine tool like milling machine was equipped with RFID tag so that it could be uniquely identified. Then workpieces such as raw materials, WIP devices, and cutting tools were bound by RFID tags. Secondly, the robots were equipped with RFID readers so that they can uh, sense various components automatically. Thirdly, vibrating sensors were deployed on the machine tools whose real-time monitoring working could be achieved. And fourthly, each of the workers, like the machine operator or logistics operator, they were carrying a smartphone by which has the functionality of NFC, near field communication. And using this smartphone, the smartphone works like a RFID device, RFID reader, which is able to sense the manufacturing objects which on the attached RFID tags. And moving on, the second step was deployment of the communication networks. Now, different communication networks were used for different purposes, like NFC with 13.65 megahertz was used for communication between the smartphone and the tags. and the reading distance was about 20 centimeter. The wireless communication standards like Bluetooth were used for data transferring between the smartphones and a central server. Wired network were being used for transferring the data between the smartphone and a central server. And wired network like Ethernet, RS-232 and RS-485 were used for connecting the KUKA robots and computers so that their communication can be ensured. Now, third step was one second. Hmm. Third step was installation of the design system. So, an IoT-enabled real-time machine status working is designed and developed as an entire solution for the test bed. This platform uses a SOA-based implementation so that to achieve easy to deploy and simple to access fashions. After that, the path of the data models can be configured so that their accessibilities could be realized. Finally, the client-side installations such as JavaScript, user roles, authority settings, and standardized connections are set up. So this was about the cloud manufacturing shop, the creation of the cloud manufacturing shop. Then how to ensure real-time machine status monitoring. So this was achieved in several steps, several procedures which we followed. First thing was a machine operator who uses his smartphone to download the services. He has his credentials, his username and password to log in and log into his working dashboard, where he is able to check the tasks assigned or historic production records, past data records. He can check. Secondly, he can select one of the tasks from the job pool, and the task associated information will be downloaded from the cloud so that he can check the job instruction, technical features, and quality criteria, etc. Third, after that, he approaches the assigned machine and uses his smartphone to uh, de- detect the tag that is deployed on the machine for indicating the attendance. After the attendance, some critical information such as the required cutting tools and materials will be sent to him from the cloud, and then he uses his smartphone to sense the required items from the specific location, and he picks them up for the task. So, let's see the slide. Yeah. So fifth step, now he installs the cutting tools with vibration sensors attached to the machine and fixes the workpiece by clicking a button on the mobile app. After processing, he presses a button on the app to inform the completion of the task, and another task will be updated on his smartphone instantly. The finished workpiece will be sent to the robotic assembly workstation. The worker uses a smartphone to detect the workpiece, places it on the conveyor, and finally the robots can detect the required workpiece and pick up for final assembly through IoT facilities. Now, within the cloud manufacturing environment, the previous mentioned challenges are addressed. How the challenges are addressed that we are seeing in this slide. Crucial production data is being captured and stored accordingly. Now there are two types of information which are very critical. First is the IoT enabled manufacturing objects whose operation and behaviors are clearly identified and captured. Such data could be used for evaluating various performances and generating statistics, analytic reports, etc. Second is real-time cutting tool status, specifically the vibration information in this paper. And using this data, the real-time machine vibration status could be monitored. The two types of data are graphically organized using some web components for end users. For example, machine statuses like starting time, ending time, and vibration, current, and processing tasks could be visualized by the data chart, curves, bar chart, etc. And by making use of the previous data, the machine performance could be achieved based on the dashboard view. And finally, it answers the 5W questions as proposed by the uh, and, finally, the 5W questions could be answered by the proposed platform.
In conclusion, we can say that this system will give us a large will give us an opportunity to save on investment and inventory space by sharing manufacturing resources. This becomes possible on large scale when we are able to identify each manufacturing resource uniquely through the RFID tags and also know their status on real time, whether they are being used and how long they are going to be used. Second advantage this work provides is a playbook for real time monitoring. The hierarchical architecture that we have provided gives a feasible implementation framework which can be used by manufacturing facilities to make a transition to an IoT and cloud based manufacturing system. We have also provided a detailed example of how this system can be deployed in a typical manufacturing shop through the case study. Some exciting areas of research for future where we can generate further improvements in this model are behavioral model for sharing manufacturing objects, in the sense that we know that we can use the real time status of each machine component to share them, but it needs an input from the manual side where people make the decision on how to share them. That decision making is something which can be further explored. The data this model provides gives a lot of opportunity to make production optimizations. That's an area which can be further researched. That's all. Thank you.